some simple announcement. If you need help and if you see somebody wearing red color name tag, then you contact them. And lunch is same place where you had the breakfast. And those who don't know, it's just a building across lecture hall on the ground floor. And the poster sessions will be on the first floor. So those who want to put up their posters during lunch hour, you can go there and put up your posters during lunch hour itself. Okay? And so now I hand over the floor to Manik for questions.
Yeah, welcome back once again. So while taking question, I will be a little bit biased. First, I will take questions from young faculties and students particularly. So first, Shreya Banerjee, she has some question. Shreya, can you go to the, is she there? I see. Okay, Gaurav Banerjee, you can go to the mic and ask your question.
Change of reference frame. So what if the two measurements are such that their time and space coordinates are such, if we want to move to a reference frame so that the order switches, we would have to travel with a velocity higher than light. If the space-time coordinates of the two events are such that they are not causally connected, then this ordering can't be switched. So in that specific case, will that theorem still hold?
Now it should be working, yeah. Okay, well, thank you for the question. So indeed, in what I'm presently, by the way, I'm speaking a little bit before you hear it. And so this is a kind of very normal way of signaling or communication. And in this case, you can still violate a Bell inequality, but the interpretation of such a violation would be very, very different. And there is also no reason to expect that the bound of the CHSH inequality of 2.
Through a very practical scenario, I couldn't really understand that part since C is isomorphic to R2. How does mathematically it becomes, necessary to incorporate quantum numbers into the mathematics? Because R2 is isomorphic to C.
Yeah, you are right, of course. I mean, D complex dimension is isomorphic to 2D real dimensions. So indeed, it is quite surprising, and it's good that you don't really understand it, and because it's very far from obvious. But the idea is that, you know, when we go to complex numbers, we introduce this imaginary unit, I. But we could, of course, also use minus I. Minus I squared is also minus 1. So there's no difference using I or minus I. There's a choice. And if you have now two independent sources, you know, the one between Alice and Bob and the one between Bob and Charlie, and you assume that they are independent, this assumption somehow means that they cannot decide that they both are going to use plus I or both use minus I. If they cannot, you know, coordinate, then you cannot guarantee that possibly one is using I and the other one is using the other convention minus I. And in this case, you get maybe a feeling, an intuitive feeling that there might be a challenge here because they cannot coordinate about the choice plus or minus I. Of course, what I'm telling you now is not a proof. The proof of the theorem is quite complex. You have to go to the paper and even to the supplementary material. It's not a trivial theorem, not something that you can understand or be convinced of. But maybe the intuition is a bit what I just told you. We cannot decide, are we going to use plus I or are we going to use my sigma y? I mean, often that is done. And then the same result would hold.
Thank you, sir. Thank you.
Yeah. Shreya, can you come and ask your question?
Might be a pretty trivial question, but I'm still going to ask it. So we were hearing from the experiment side that the experiments are performed for proving that hidden variable model is not valid. Now, my understanding, it might be wrong, but my understanding of Bell's inequality tells me that the mathematics of it is sound, and the way I was looking at it before hearing today's lecture about the experiments, that they kind of validate the quantumness of a system that people are generating. So how do you kind of merge these two? Does the experiments really validates Bell's theory, or Bell's theory validates that experiments are being in the quantum realm?
I will give the word to Harald, but maybe just one thing. You're talking about hidden variable. It's hidden local variable. Yes. Whether they are hidden or not, we don't care. But whether they are local or not, this is the essential issue. And then, okay, Harald will elaborate on that. But in it, if you would have done one experiment, no one would believe in it. It's only because we did, I don't know, hundreds or maybe thousands of experiments over the entire planet that we, the physicists, the experimental physicists, are now convinced. Maybe you want to elaborate on that.
No, I guess there is, perhaps I've misunderstood your question, or you misunderstood this concept, but I mean, we do not, I mean, the violation of a Bell inequality does not mean that Bell was wrong. I mean, it's just that he put up this inequality just to get this distinction between local realistic theories and quantum physics.
Yeah, no, so that was not my conception. So I know that Bell's violation of Bell's inequality means that the system doesn't obey the local hidden variable models, and it's quantum. Let's call that quantumness, and it's quantum. So my question was like, so when you do experiments and you are closing these loopholes, do the loopholes associated with the theory or the experiments?
With the concept of deriving the Bell inequality. So, I mean, you have some requirements, and you have to fulfill all the requirements in your experiment.
Okay.
And that's it. I mean, to really show that your observers, for example, are independent, space-like separated. I mean, you really have to show this in order to close the locality loophole.
Okay,
or in order to close the detection loophole, etc., etc. You have to follow some restrictions, and then you can say you close this loophole.
Okay, sir. So to summarize, so Bell had some assumption based on what he derived the theory, and through experiments, in reality, all of those are probably not possible, but you try to close them one by one. Is that it?
Yeah, but I mean, in the moment, they are more or less closed altogether in one experiment. So, I mean, the experiment by the Chinese group, I mean, it almost was there. You can interpret now where the randomness comes from differently, perhaps, but yeah, it was quite nice.
Thank you, sir.
Maybe just to elaborate a little bit more, when an experiment violates a Bell inequality, that indeed, provided it's all done properly and so on, that falsifies local variables, but it doesn't mean yet that it is quantum. But that what every experimentalist does, and you have seen it on all the graphs that Harald has showed, is not only the experimental data, but you always had also this continuous curve, which is the theory. But this is not the pure theory, it's the theory corrected by all the known imperfection in the experiment.
Okay.
And it is because the experimental point really follow this line. Not only do they violate Bell inequality, but they really sit quite well on this vertical line, taking into account all the known defects of the experiments. This is really the strong support of quantum mechanics.
Okay. Okay. Thank you, sir.
Next is Kolahal Bhattacharya. Is he here? Yeah.
Hello, sir. Good morning. Actually, my question is for Professor Gisin. So today, when you were giving the lecture, you mentioned that there is a question like, how does nature do the trick of entangling the two states that we are observing as individuals? My question is perhaps a bit from a separate perspective. So we also talk about non-locality in the context of the Aharonov bomb effect. And in that context, in that context, we do not talk about the entanglement of quantum states as such. So do you think that there could be some connection between these two, or can we understand or view the quantum entanglement sorry, from in the light of the Aharonov-Bohm effect? That is the question.
Yeah, thank you. Thank you. Again, a very good question. There are several sorts of non-locality, and the AB effect, or the Aharonov-Bohm effect, is more dynamical effect, while the kind of effects that we are interested in celebrating Bell today, this is more a kinematical effect. So it seems to be quite different kinds of effects. Are they correlated? Maybe in the sense that if we would find a good story to explain how nature does one, then the same kind of story would also explain the other ones. I don't know. I don't think so, but actually I don't really know. I think it's a good question. Again, it's a different sort of non-locality, and so possibly there will be different explanations or stories to tell both kinds of non-localities.
Okay, thanks.
So, Professor Tejendra Pratap Singh, you have some question.
Wait. Yeah, here it's coming.
Yeah, thank you for two very nice talks. My question is for both of you. It's about these so-called supra-quantum non-local correlation, just to share with the audience. In the CH, you know, of course, in the CH-SH inequality, there's an upper bound for quantum non-local correlations, which is 2 square root 2. But Popescu-Roerlich showed that relativity allows a higher bound of 4. So for me, this gap between 2 square root 2 and 4 is extremely puzzling. And what we found, I want to share with you what we found and then ask you my question. There's a generalization of quantum theory due to Stephen Adler known as trace dynamics, where he tries to derive both the unitarity and the reduction aspect from one underlying theory. And one of the principles of trace dynamics is that, to begin with, the quantum commutator does not hold. The Heisenberg commutation relation is not imposed beforehand. The QP commutator is arbitrary. In certain approximations, it becomes a quantum commutator, but otherwise the theory is more general. So what we found, that if I look at the CHSH inequality in trace dynamics, when you recover quantum mechanics, you get the Cyrilson bound. But so long as the quantum commutator is not QP equals IH bar, you can violate the Cyrilson bound and go towards Popescu-Roerlich. So for me, that's a bit comforting. It shows that there's a more general theory which is trying to sort of remove this contradiction between quantum mechanics and relativity. My question is, for those of you who test Bell's inequalities, if I came up with a theoretical model saying here's a violation, could you kindly check experimentally if this is correct or not? How does one go about it? Or are experimentally supraquantum correlations ruled out? If not, what should we do to test for them? Thank you.
Yeah, maybe I start first and you can continue. No, I think it's, again, a very good question. So there's no reason to believe that quantum is the ultimate theory. Actually, I don't believe that in the existence of an ultimate theory. We'll make endless progress. But so how are we going to do? As I answered before to this lady, when we do an experiment on Bell inequality, not only do we violate Bell inequality, but we also really check that we really find the points, these experimental points, really where we expect them. So we also confirm quantum mechanics at the same time. Now, if there would be a post-quantum theory, for instance, one that would allow to violate this Cyrilson bound of 2 square root of 2 to go to 3.5 or whatever number, then, I mean, if that kind of post-quantum theory would predict this higher value of the violation for the same settings than the ones and the same kind of experimental arrangement than the ones that we are using today, then we probably would have seen it, because then the experimental points would be higher than the theory curves, and we haven't seen that. But maybe these post-quantum theories will tell us that we need to do different kinds of measurements. You know, if we have a new theory, there will be maybe additional variables, not local variables, but additional variables, additional non-local variables. I mean, you know, super spins or whatever, intrinsic variables. And maybe someday we'll be able to measure them, and then maybe someday we'll be able to go beyond these 2 square root of 2. However, I'm not very optimistic.
One quick remark I forgot to make. It seems to be happening at high energies around the TeV scale. So I wanted to ask, how about doing Bell tests at colliders, which I know some people are talking about? What the prospects there? So, yeah.
Okay, so just 2 things. So first, if you really go beyond this 2 square root of 2, there's one point where you collapse the communication complexity concept. So this is, okay, I'm not sure I can explain all that, but there is some kind of concept that comes from computer science, and that at least from a computer science perspective seems completely obvious. And so these people would tell you it's impossible to collapse communication complexity. And it has been proven by Gilles Brassard and many co-authors that going beyond 2 square root of 2 would collapse this. So it is not a proof, but it's an argument showing that it is unlikely that a post-quantum measurement theory would allow you to go beyond this 2 square root of 2. That's one point. The other one, if you want us to do an experiment in high energy physics, for instance, or anything, we need some model. I don't expect a complete theory, but we need at least that the theories give us some hint where to look at. Because, you know, the number of parameters, the number of things we can do in the lab is essentially infinite. We can trigger in all kind of directions. But we need a kind of a flashlight so that we know in which direction to look. So tell us which direction and have some kind of idea why this is kind of plausible, so at least have a kind of model. And if we have a model telling us you have to go in that direction, then Harald, myself, and all the other experimentalists will try to look into that direction.
Yeah, it's the same. I mean, so far, I mean, we are observing with operators which commute. Okay, so I mean, then which don't commute. Sorry, which don't commute. I mean, according to Heisenberg, etc., etc. So we are measuring polarization, for example. I mean, that's just Pauli spin matrices. So therefore, it's not a big surprise that we have this Tyrolson bound. So really, if you can show us which operators really we could measure, I mean, we would immediately run to the lab, no doubt. But I mean, it's really, we need this new type of measurement, honestly. And then we can continue.
Particle collider experiments, particle collider, how are they doing, do you know? I mean, I see a lot of papers coming out, but has there been an actual Bell measurement, say at the LHC or some such thing?
I guess so far what I know is they are still also only observing in all the standard bases, if you want to call it like this, in the standard properties with the standard very regular operators. And therefore there is no chance ever so far to see a violation now already.
That's like saying a priori assume that quantum theory is correct. And
I mean, if you tell us again, if you tell us what measurement we can do, we'll do it.
okay, thank you.
Yeah, Professor Guru Prashatkar.
No, I am asking my question later,
Hi.
but in this context, I am making some comment. As Professor Gisin told that if the violation is forced, then communication complexity problem will be trivial, and people believe that it cannot be done. And they have some proof also that if it goes beyond certain level, then communication complexity problem becomes trivial. But there are other thing, like there is some principle called information causality principle. It is slightly stronger than no signaling principle. But that definitely tells that if the violation of Bell's quantity is more than 2√2, then its information causality is violated. So information causality, at least if you believe that it is principle of nature, then you have to accept also that violation will be 2√2. And it is totally independent of any algebra.
We don't have just special relativity and quantum theory. We have something more.
Yeah.
Yeah.
Yes, but I mean, I guess this information causality was just derived on the basis of the standard operators. So I mean, if there would be new ones, I would not be surprised that the whole
No, but
proof,
information
does not
causality
hold
just
any longer.
a statement about nature. It does not depend on algebra. It is some statement like no signaling is a principle. It is also a principle. So based on this principle, it has been derived that quantum mechanics obeys it, classical world obeys it, and if there is some violation is 2√2 plus epsilon, then actually information causality is violated.
I suppose we showed, like in trace dynamics, that the Peterson bound is violated. So you are saying trace dynamics violates
Information causality principle, yeah.
Yeah.
Of course, it has not been accepted like no signaling condition. No, all the scientists at least believe in no signaling principle, but there may be some scientists who may not believe in information causality principle. Yeah, that's all.
Yeah, next question. Next question is by Manavendra Bera.
Shall I go to that point or from here itself?
Yeah, or can one more volunteer can come with?
Well, I can just come here. So first of all, thank you, Nicolas and Harald, for these wonderful presentations. So I will start with some simple questions so that we can stimulate some more engaging discussion. If I look at Bell inequality, obviously it starts with this assumption that this locality and realism to be respected. In Bell's language, it is local causality rather. So in today's time, if I ask that after violation of Bell inequality, which of these assumptions are to be discarded or both of them? And if we are to choose one, why? And if not, is there any way to check one by one, whether, just to check whether the realism is violated or the locality? Is there any answer?
Yes, I don't think that there is an answer in the moment. And I guess if you ask us now which we want to drop, it's like what tastes better for us. Like, do you prefer chicken or lamb? Okay, it's everybody is different in that respect.
I would have a quite different answer. Locality is well defined. It is factorization of probability. So this is an assumption that you can formulate, and hence you can also test it. Realism here, I don't even understand what kind of assumption is that. I don't think there is any assumption about realism. Again, this lambda is not a kind of, old-fashioned local variable. It is the state of the system as described at any possible future theory. And I believe in future theories, or in post-quantum theories, but these post-quantum theories, if they are still physics, they will still make predictions. Predictions at least about probabilities. And so it's not a realism assumption to assume that there is a lambda. Lambda just means that we can continue to do physics with predictions. So for me, this is not an assumption. This is a given that we can continue to make physics. And so obviously, between locality and realism, I'm obviously giving up locality, because if I would give up realism, I would have to change my job. It's too late for me to change my job.
So in this continuation, I have a couple of more questions. In this continuation, see, all these what we are looking at obviously are based on classical probability theories. If someone come up with, for example...
No, sorry. Remember my very, very first slide. I had a P given psi, the quantum state, of AB given xy. This is quantum probabilities. I'm using the quantum formalism in standard Hilbert spaces with operators, state vectors, and all that. This is quantum probabilities. And these quantum probabilities do not factor. It's not a matter of classical probabilities. The quantum probabilities do not factor.
Okay, so thank you for this answer. The second one, and I think you have mentioned it in case I missed. So you actually mentioned that obviously with the violation of Bell inequality, we give up local hidden variable theories and also non-local. In the context when you talk about some directional, this causal direction.
Deterministic non-local variables.
Deterministic. So in this point of, or let's say standpoint, how would I look at Bohm's hidden variable theory, and what would be your stand on that sense that it is going to survive or not?
Yeah, well, so maybe two answers. So first of all, Bohm's theory would certainly not satisfy this covariance assumption, you know, that if I look at the experiment from one reference frame or from the other reference frame, Bohmian mechanics is not at all relativistically friendly or friendly to relativity. So it somehow needs a preferred reference frame. So that's why the theorem which I presented, excluding deterministic covariant non-local variables, still holds and is compatible with Bohmian mechanics. The second thing about Bohmian mechanics, it assumes somehow that there is a hidden influence, something is going on behind the scene, but according to Bohmian mechanics, this thing that goes behind the scene goes at infinite speed. And okay, maybe you know that I don't like infinities, especially not actual infinities. And so Bohmian mechanics is kind of course, it's an existence proof. You have non-local variables. That is a logical possibility. But if you have to assume first that it's against relativity, even against special relativity, and it goes at infinite speed, so if I do anything here, in the entire universe, all the galaxies where instantaneously it changes, that's total nonsense to me. So even there is a logical possibility here, it's not a one that I find attractive enough to spend time on it, personally.
Harald, do you have any other point to add here?
No, I mean, because I guess we do not know much about space in order to say where the influence would go next. I guess that's the first thing to solve here, where the infinity really is and the large distances, what we see.
Thank you. The last piece of question, okay?
Yeah, short one.
Yes. So obviously you have shown that the use of imaginary number in quantum mechanics is not a luxury in the sense like it is essential, it's not a tool. So from that point of view, on the foundational perspective, what really it adds?
Well, I think it's, numbers are extremely important to understand how nature does it. Now, of course, we started, 10,000 years ago more to count sheep and to count, hectares and so on. And then we used real numbers. Newton introduced calculus, and we needed real numbers. And then numbers kind of by mathematicians got developed by themselves with complex numbers, so that every algebraic equation has as many solutions as the degree of the polynomial. And then you have even quaternionic numbers and octonionic numbers and I don't know what, so on and so on. But since Newton, real numbers were always sufficient. So, before calculus, integer or maybe rational numbers were sufficient. Then we needed real numbers. And then we know that we sometimes use complex numbers, but just as a tool. It's a convenient tool, but it's not necessary. And from the very beginning, quantum mechanics used complex numbers. And already Schrödinger was asking, but many more people, Ehrenfest also wrote about that, do we really need these complex numbers, or are they just convenient? And until, 3 years ago, people were really thinking that, well, in quantum mechanics, these complex numbers are also just convenient. Or someone said before, a complex Hilbert space of dimension d is isomorphic to a real Hilbert space of dimension 2d. So it looks that complex numbers are just convenient. But once you go to this kind of network where you assume independent sources, you can have one source of entangled photons which is powered by solar energy, and the other source is powered by a university professor on a bicycle. Now, you can always say that the sun and the professor are correlated, but that's not an explanation. There is no explanatory power in claiming that the professor on his bicycle is correlated to the sun. So they are independent. We have to assume that they're independent. If we want to gain any understanding, we have to accept that they are independent systems. And if they are independent systems, then you can prove that predictions made by real Hilbert spaces, real number Hilbert spaces, just cannot match the predictions made by complex Hilbert spaces. And so this I find really very, very fascinating, and I think it's very deep as a result. For the first time in the history of science here, we really need complex numbers. We cannot do everything with real numbers. It's a major step, in my opinion.
Thank you very much.
Yeah, Harald want to make. Sorry.
May I ask a question as well? Or?
Sure.
So, to whom? Yeah, perhaps to everybody, because I'm experimentalist. I don't know that so well. For electrodynamics, don't we need complex numbers as well, unless this trick that we have a phase difference between sine and cosine solutions? And the next question is, why don't we need these quaternionic numbers for quantum physics?
Okay, so for the first question, Harald, in Maxwell's equations, you don't have I in it. No, you don't have any I, so this is a purely real number thing. And the reason we use complex numbers in electrodynamics, or more generally, as soon as you have a wave, you have this cosine and sines, and then you have this magical formula that e to the power I n phi is the same as e to the power I phi to all to the power n. And this then translates into all the known trigonometric functions. And this is just a very convenient way of even remembering all these trigonometric relations. But this is just a trick. You don't need it. You can just remember all the formula you had to learn in your high school, yes, and that's enough.
But it's like your single qubit, what you can add this r squared, and you cannot do it for multi-qubits. So for the single qubit, therefore it works for the electrodynamics, I guess.
Yeah, you can say it like that. But it works even if you have only one source, even if you have many qubits but only one source. As long as you have only one source, it will work, and then you can say quantum mechanics is like electrodynamics. But if you have several sources and you assume that they are independent, then it will no longer work. And indeed, then maybe this is the kind of independence that goes beyond Maxwell. Now, for the quaternionic Hilbert spaces, they also exist. Now, I don't remember exactly what is the argument, but there are also some good arguments why
I think
we should not consider them, but I don't remember why now.
Triple slit experiment by Perez has some argument that if quaternion, this triple slit interference pattern should not come.
Yeah, okay. Okay, so, but it's a different argument.
Yeah, but the Dirac equation uses quaternion indirectly.
Yeah, but okay, but this is not okay. This quantum field theory and these kind of things, you will have that. Yeah.
Yeah. So in continuation to that, I have some just quick question regarding little bit technical. So when you want to establish that real number is not sufficient, you want to prove it as a device-independent way, looking into only the statistics. So as less as possible structural assumption we should take. But in your derivation, aren't you taking the assumption that composite system, the description, satisfy local tomography?
No, we don't assume that, but we assume the tensor product structure. So tensor product structure is indeed assumed, so it's not completely device independent. I don't even exactly understand. If you want to do something completely device independent, you should not be speaking of Hilbert spaces. Mm-hmm. Yeah. And so if you don't speak about Hilbert spaces, you cannot exclude some specific Hilbert spaces.
Yeah.
Maybe in the middle there is one question.
Yeah, Urvashidi.
I just wanted to comment on the point that Manik just made. So the triple slit experiment is not the Perez test. The Perez test is based on the superposition principle.
No, but Perez 1970s paper, this quaternion versus...
That's correct.
Yeah.
So I haven't finished my comment. So Perez test actually does tell you how to rule out between real, complex, quaternionic, and anything beyond. It's based on the superposition principle, and it in fact uses the phase as a very critical ingredient to formulate the test. The triple slit experiment tests the Sorkin test, which is based on the Born rule. So these are fundamentally different tests, and the triple test has nothing much to do with quaternionic theories, whereas Perez test does, but based on very different principles of quantum mechanics. And because this is now raised, and Lee and I have this very unenviable job of talking about testing foundations of quantum mechanics with light, we can talk about anything we want. So I will show one slide on this Perez and Sorkin. And Sorkin will be anyway there, but the Perez test I will definitely show one slide just so that people have the right reference. Yeah, that's it. Thank you.
Yeah. Next is Dipankar Da, you have some point to say. Yeah, you can ask.
First of all, Nicolas, about that point, one of the questioners raised about which one to rule out, locality or realism, or what is the option we have. Of course, you have your famous paper on this issue, and you in your talk you referred to that. But I think the reference to that, the discussion of you, because of the paucity of time, was incomplete. So I would just put it in some proper perspective, some more detailed perspective. So what you are considering, if one considers stochastic derivation of Bell inequality and impose locality condition as a factorizability condition, then in that derivation of Bell inequality, it is hard to see where the input of realism comes. And so based on this derivation and this way of looking, one may argue that one has to reject locality. That is the only option you have. And Bell's theorem, put it this way, has nothing to say about realism. But there are some caveats, like you also hinted in that article, and I'd like to bring it up here for further discussion, is that an underlying subtle assumption in that derivation, where the input of realism comes, is in the assumption of reality of outputs and reality of inputs, in that sense. So you assume that the choice of setting is perfectly freedom of choice, that is the freedom of choice, and the reality of outcome. And as you had also argued in that article, and I also share your view, that freedom of choice we have to make to do reasonable physics. Then the only option remains is to consider critically the assumption of reality of outcome. And there the interesting question comes where the non-locality issue gets linked to the measurement problem, that when does a measurement get completed? And some of us who are very much addicted to quantum measurement problem find it a bit disturbing that in all these discussions of experiments and tests of hidden influence, the question of where the measurement is completed, that is a critical point, but that is overlooked. Because all these time bounds and all these you are putting, it could be that the signal really goes at a much later time than that. And so we don't know yet unambiguously when to define a measurement. That issue did not come up in this entire discussion.
Yeah, thank you very much. Of course, I like your comment very much, but you are a bit too fast.
Okay.
As you know, I have a second talk tomorrow.
Okay.
And actually about the measurement problem. And so tomorrow I will exactly address the question that you just raised in the second part of your comment. So just wait a bit for tomorrow. But I agree, indeed. We assume when we do, well, any experimentalist, Harald, myself, but I don't think there's a single experimentalist who doesn't believe that measurements have outcomes.
Yes.
Your measurements have outcomes. Now you can always say maybe the outcome comes a bit later, only once it is, I don't know, in my brain, or only once it is registered by a computer or whatever. So, but I address this question tomorrow, so let's wait for tomorrow. But let me just say, so indeed I have this paper, Anti-Realism, deep thought or a soft option, which is a very short paper, which I would certainly recommend to especially the younger persons here in the audience, in which I try to derive Bell inequality without any reference on realism, and say, okay, so it is locality the issue. The remaining open possibilities, logical possibilities, would be either that we give up, free choice or measurement independence. It's just a different way of saying the same. So you could say that these inputs X and Y are actually correlated to the lambda, to this hypothetical local variable. But then, of course, that would essentially be the end of the possibility of doing experimental sciences, because it means that Harald can no longer choose which experiment to perform, which is, it's a logical possibility, like solipsism is another logical possibility. There are infinitely many logical possibilities which are totally uninteresting. So we should not spend time on the uninteresting things. There are enough interesting things to do. The other possibility is indeed, as you said, that the measurements outcome, they happen. Again, it's ridiculous to argue against the fact that measurements have outcomes. But when do these measurements outcomes are really there? This is connected to the measurement problem, the quantum measurement problem. And again, here I will talk more about that tomorrow.
But the point I was making that this issue is also closely then related to the issue of testing non-locality or putting bounds on the hidden influence. In that sense, one can say that the entire issue of non-locality is linked with the measurement problem. So those who argue against quantum measurement problem being irrelevant conceptual curiosity.
After my talk tomorrow, no one is going to...
No, that I know, but from a pragmatic point of view also, I'm saying those who believe non-locality is a fundamental issue, they have to also confront the measurement problem. This is a point I was trying to stress.
Concerning your question, when we call a result now a result, I guess I heard the argument first from Nicolas anyway. It's such that you cannot clone quantum states. So the moment I can make copies of my results, I could say that now they are classical, because I can copy any classical value and so on. And therefore, I guess you can still say I can reverse all the result, but I mean, if I can make copies of a result, then most likely it's classical. And that's actually how we define the duration of our measurement.
Okay, we can have more discussion tomorrow on that. And just another point, that non-locality is a fundamental feature of nature which you emphasized. And another recurring theme of your talk has been that there should be, physics is all about telling story. So if I phrased it that way, then relativity is a story in space-time, but non-local correlations have no story to tell in space-time. So how does one fit non-locality, this non-local correlations, the quantum non-local correlations within a really relativistic framework? And particularly field theoretic or even relativistic quantum mechanics, because we had to also work at one time, and there were many puzzling results if you apply these quantum correlations in the relativistic context. So what is your view? That should be one of the next exciting things that may be happening in the next.
Yeah, indeed. I mean, I think this is now a well-accepted fact, well accepted by all the physics community, that there is, well, it's something in between a tension and a contradiction between relativity and quantum mechanics. And so this comes under the terminology of quantum gravity, and there are huge research projects and several ideas how to solve this quantum gravity problem. But clearly today one can say that no one has any good idea, and we don't make huge progresses on that. I mean, maybe some people will get annoyed if I say that, but a real progress would be something that makes predictions that we really see in the lab, and we are very far from that. So there is a tension, and it's good news for all the youngsters, because there is plenty of things to be discovered.
Yeah,
I
please.
prefer to live with open questions than with, claims of answers that are not actually that consistent.
Yes, sorry, I cannot resist saying again what I talked to you over tea time, how to tell the quantum non-locality story in space-time. So some of our work suggests that if space-time is 6-dimensional and the 2 extra dimensions are time-like, not space-like but time-like, 3 times and 3 space, then events which are local in the higher dimensional space-time can look non-local, as we find, when projected to our 4D space-time. And we are quite excited about this idea and how to test it experimentally. We just talked. So what is happening is that there is a shorter path in the higher dimensional space-time through which the signal arrives at the speed of light. And what that means is that if Alice makes a measurement and Bob makes a measurement very quickly after Alice, there will be a factorizability of the probabilities and Bell's inequalities will not be violated. To observe the violation, you have to have some finite time interval pass. I don't know how finite is that. I don't know. We have to work on that. But that seems one way to test this idea, that if Bob measures very quickly, he will not see a violation. Yeah, thank you.
Yeah. So of course I agree. Yeah. So there are many ideas out there, but none of them led to any experiments so far. Now what you are telling me is that there might be an idea of an experiment which is very close to what I said at the end with my hidden influence. Yes. And that we should do this experiment. And I mean, again, tell us what kind of experiment we should do, which is the bounds for this, the speed of this superluminal hidden influence, and Harald or myself or someone else will do the experiment. We'll be very happy if you make predictions.
What might turn out disappointingly is that Bob has to act within 10 to the minus 33 seconds of Alice.
Well, but that will depend on the distance. Even if it is crazy numbers, someday there will be an experiment, a Bell inequality violation between, I don't know, Alice on Earth and Bob on the moon, or maybe Bob will be on Mars. And then even some numbers that may sound crazy will become feasible. But at least we would have a target.
Okay, I agree. Yeah. Professor Group.
Let's go back to the more junior guys.
Yeah.
It's for Professor Gisin. So Bell's inequality was historically derived based on the assumption of local realism. But the same Bell's inequality can also be derived in the operational level if you assume no signaling and impossibility of joint measurement. So when Bell's inequality is violated, then we tell that joint measurement is not possible. But you have some examples where you have taken 3 parties and just single measurement on each side, which also shows some non-locality. Then I am curious that these basic points that there should be at least 2 observables which cannot be measured jointly, this is not needed. So I am thinking whether this independence of this preparation between Alice, Bob Alice and Charlie Alice, whether it is a very strong assumption, or the middle one will perform some measurement which is in the entanglement basis, whether it is giving some power. Push-Barrett result has been, this PBR result has been criticized because of preparation independence. I am thinking whether the same may apply to your result also.
Okay, so indeed, I did not mention that at all today because of, limited time. But you could indeed, in this network, just imagine a triangle. So each edge of the triangle is an independent source, maybe 3 times a singlet, and then you do fixed measurements. That's what you are referring to, no, fixed measurements. And nevertheless, although you have no inputs because the measurements are always fixed, of course, they are commuting since there's only one. It commutes with itself, obviously. But you make the assumption that the sources are independent. And in this scenario, this kind of triangle scenario, you can also prove rule out local variables. So you can also prove the existence of non-locality. Now, of course, here, so the nice thing here is that you don't have inputs. So you don't have anything to do with measurement independence or freedom of choice or anything like that. You don't need this assumption. However, you do indeed need the assumption of independence. And now, I think that's again like, do you prefer chicken or lamb? Do you prefer to have inputs and now have to assume that the inputs are independent? Or do you prefer to have several sources and assume that the sources are independent? I would say it's not that one is better than the other one. I would say it's very good that we have these different alternatives and that we can, I have to say, for the triangle, I think no experiment has been done yet, and certainly not at the same level of sophistication as for the Bell inequality. But on the theory side, we have the predictions, and the predictions are very clear, and predictions is that quantum mechanics is going to rule out local variables in both scenarios, with or without inputs, but always with some assumption of independence.
Yeah, so if anybody has questions, yeah, please
come. Professor Gisin, accepting the fact that non-locality or the explanation of non-locality is something which lies beyond space-time, why not it is legitimate to construct a ontological model of our operational quantum theory such that there exists some kind of action at a distance between the ontological constituents, but that action at a distance is not available in the operational level between observers. Why not it is legitimate to construct such kind of theory?
But you're absolutely right. Yes, we can or should consider these kind of models. I mean, what we heard before with the 6-dimensional space-time, so free space and free times, this is certainly an example going a bit in that direction. What is now needed is that this model makes predictions and that we can go to labs and make experiments and either falsify that model or maybe confirm it. And also when I'm speaking about faster than light hidden influences, I'm also going exactly, I think, along the direction you are telling. It's going beyond standard space-time because I'm speaking of faster than light, so you need a privileged reference frame. So it's going beyond standard relativity or the spirit of relativity. It's not a contradiction, but it's certainly in tension with relativity. And here also
but that may not be the final theory.
No, it's maybe not the final, but we need to make steps in that direction. But think always, it's not enough to make a wild step. You need at some point to make predictions. This is physics. This is an empirical science. So you need at some point to be able to say, if you do that, then you will see, for instance, that we no longer violate Bell inequality, or you will see that we violate it by more than 2 square root of 2. But you have to tell us that there is a prediction. Maybe your prediction cannot be tested today with today's technology. Maybe we need better detectors, better whatever, spacecraft or longer distances from the dimension of the galaxy. Okay, but you need to make some prediction. But I fully agree with you, we need to be wild enough and courage enough to consider models that go beyond standard space-time.
Okay. And one second question, I want to know what is the present status of the precision test of serialization bound?
Sorry, I didn't understand.
What is the present experimental progress?
I guess you have been involved in
that direction.
I guess Paul Kwiat and Gisin paper, it's 2.81 or something like this. I guess this is really limited by technical reasons on dark counts and time resolution of your detectors. But it's close to less than 1%.
Okay.
So any more question? Yeah, please come. Yeah, you.
Hello, thank you very much for the talk. I want to make two comments regarding the result proving the gap between complex quantum theory and real quantum theory. So I found it a little bit confusing to say that this result showed that we really need complex numbers because, for example, in the framework of generalized probabilistic theory, we know that quantum theory can be represented in that framework where we only need real numbers because in that framework, all the quantum states are vectors in the space of Hermitian operators, and it is a real vector space. And in that framework, we can reproduce all the operational predictions of the usual so-called complex quantum theory.
Yes, you can reproduce all predictions of quantum mechanics using one source. If you have many sources, 2 or more independent sources, then you can no longer reproduce all the predictions of quantum mechanics.
I think that framework is completely equivalent to the usual complex quantum theory. As I said, instead of we talk about states in Hilbert space, we talk about density operators, which lives in the real vector space in the operators of Hilbert space. So in that framework, we only need real numbers to reproduce all the experimental results, including like bilocality, the correlations in the bilocal scenarios. So even when we have independent sources, if we rewrite quantum theory using the language of generalized probabilistic theory, we can get all the correlations.
Well, this is where I think we disagree, but it's not a matter of disagreeing. But the theorem says that if you have independent sources, also with GPTs, you will not be able to reproduce all the results using only real numbers.
Okay, maybe we can discuss this point later a bit more because I think I'm still a bit confused about it. The second comment I would like to make is that I feel the result in your paper, what it really showed is that we are living in a world which is governed by the theory that is not invariant under any symmetry that is represented by anti-unitaries. For example, the time reversal symmetry, because any symmetry that is represented by anti-unitaries instead of unitaries, they can always be written as a complex conjugation up to degrees of freedom with unitary. Under this point of view, the real quantum theory defined in your paper is basically quantum theory with the restriction that all quantum states, all quantum measurements that are invariant under an anti-unitary symmetry group, for example, the time reversal symmetry. So for me and some of my colleagues where we were studying this, we think that the result in that paper is remarkable in the sense that it showed that there's a gap between the usual quantum theory, which is not invariant under, for example, time reversal symmetry, and a restricted version of quantum theory, the so-called the real quantum theory in the paper, which is invariant under some anti-unitary symmetries, for example, the time reversal symmetry. And
Yeah, okay, so thank you very much. Very glad to see that many people are aware and interested by this result about complex numbers or no real numbers. I think you are absolutely right. I mean, with these anti-unitaries, essentially you are changing I into minus I. And then you can say, okay, now, you know, in the Schrödinger equation, if you change I to minus I, it's the same as changing t into minus t. So indeed, you go time reversal. And indeed, now you need to decide, is Alice and Bob going forward in time? But then Bob and Charlie should also go forward in time. Now, if you describe one going forward and the other one, the second source, going backwards in time, again, intuitively, you have to see that there will be a tension, there will be a problem. Everything has to move forward or everything has to move backwards, but you cannot have half of you cannot describe your experiment with half of it going forward in time and the other half going backwards in time. So that's, again, the intuition behind all that. But I think essentially from what I understood of your comment, I think you are just absolutely correct. And there is indeed this deep connection. And maybe there is even something deeper than that. And that I'm not sure that what we did in this paper exhausts all the questions. For instance, another question, just to mention that there is more to be done there, is something that we are working on in Geneva, but there is still room for plenty of improvement. So we assume that the two sources are completely independent. But you could assume that they are partially independent. Of course, if they are totally dependent, then you can just double the dimension of Hilbert space and you can do everything with real numbers. But let's suppose they are just epsilon independent, just a little bit independence. Is it enough to have epsilon independence to rule out real numbers? I don't know. My intuition is yes, it's sufficient. That's my intuition, but this is not a proof, of course. So just to say, and that follows from what you're saying, this result, which is quite new, and okay, here apparently many people are already a bit aware of it, I think there is still plenty to do based on this new result. And so I would certainly encourage you, or maybe you can write something or develop your ideas on this time reversal and connection between these complex numbers and anti-unitaries. Yeah, I would not be surprised that you find nice results there.
Right, thanks. And maybe one thing I should add is that what we found is that if instead we have a unitary symmetry, and we demand that we restrict our quantum theory to only contain states and measurements and transformations that are invariant under unitary symmetric group, then actually there's no gap in terms of the correlations in the bilocality scenario. It is only when the symmetry group is represented by anti-unitaries, then we see the gap. Therefore, the intuition you mentioned that, okay, we have a lack of reference frame regarding whether time is going forward or backward, is maybe the reason why we have the gap. I think the intuition there should be, maybe it needed to be much more nuanced, because if the symmetry is a unitary symmetry group, we also have the lack of reference frame narrative, but in fact, there will not be gap. It is only when the symmetry that is anti-unitary, then we will see a gap between complex and between the full quantum theory and the quantum theory that is restricted under the symmetry. And yeah, I totally agree with you that there are much more interesting things to further explore following your work on this thing. Thanks.
Yeah, thank you. If you write something, please send me a copy of your paper.
Thanks very much.
So one last question here, please. Please, yeah.
I just have a small question, the experimental one. So you mentioned in your talk this one, semiconductor single photon source. So does it test the Bell inequality violation up to the Sadelson bond?
What semiconductor single photon source did you
Yes,
have?
yes. You have mentioned in your talk.
The detectors, or what?
Yes, yes, yeah.
The semiconductor detectors.
Yeah.
And what's wrong with them?
So does it test the Bell inequality violation up to the Sadelson bond?
Up to the?
Sadelson bond.
Sadelson. Yes, that was used for these experiments. The non-SPDC source. I guess there was nobody saw any difference between using one or the other detector so far. No, but I mean there was no. I mean I guess nobody reported that there would be. Nobody reported so far that there would be a difference with from observing with a superconducting or semiconducting detector, even a photomultiplier for that purpose. I guess we don't know about any of such experiments.
Okay, thank you.
Okay, since Shomitra said we can continue this session a little bit more, yeah, last, yeah.
Wait for the microphone so that we can hear.
Thanks. I have a small comment about the question of using the imaginary unit I in quantum mechanics. Like a few years back, there were two papers in American Journal of Physics by Ricardo Karam. So it's very fascinating that I got to know that Schrödinger himself, he was not really happy with Schrödinger's equation. And a few years later, he came out with a new Schrödinger's equation, which is a fourth order equation, where he did not have any I whatsoever. So, but eventually he realized that it is not describing the quantum mechanics correctly, and he came back to the original version of Schrödinger's equation. Last year, what I did is that I asked one of my students to check that fourth order equation to like on a simple problem, like particle in a box and something, like simple problems. So what he found is that when he uses those fourth order equation, then not all the eigenvalues are faithfully getting reproduced. So this is an observation I had made, so I just wanted to share it.
Yeah, I think actually it's quite interesting that, Schrödinger was not happy with the Schrödinger equation. Bell was not happy with the Bell inequality because he wanted actually locality. Clauser was not happy with the result of his experiment. So this is really science. Very often, you have some intuition, you would like to see something, you do the theory, you do the experiment, but at the end, it's nature that tells you the answer, and you may not be happy in the sense that nature is not always supporting your intuition. Sometimes you have to update your intuition and learn from the lesson that nature gives you. Yeah, there are many. We could make a huge list of people who did a tremendous important work and were at the end not happy because actually this is not what they wanted. But it's not, fortunately, it's not the experimentalists who decide about the results. Measurements have outcomes, and the outcomes are not chosen by the experimentalist. The experimentalist can choose which measurement to do. We choose the X and Y, but we don't choose the A and B, the outcomes.
Yeah, Girish. Yeah, you can use that.
Can I use that? That's okay. Yeah. So I have a comment related to Harald's question on whether classical electrodynamics also requires I. So, Nicolas answered this question by saying that Maxwell's equations don't involve the imaginary I. But I would argue that that's because Maxwell's equations are formulated in terms of the electric and magnetic fields, but you could have an alternative formulation in terms of the Riemann-Silberstein vector, which is defined as E plus IB, and that again naturally gains the imaginary factor of I. So my question is, this Nature paper of 2021, does it rule out only the real vector space formulations of quantum theory? So for instance, I'm thinking of maybe the path integral formulation of quantum theory where, it naturally transitions to classical physics when h bar tends to 0. So you recover the Euler-Lagrange equations. And that doesn't seem to involve I very obviously and inevitably. So I would love to know your comments on that. Thank you.
Yeah, so clearly you can write Maxwell's equations in a formalism where you use I. But the important point is you don't need to. There is a way to write Maxwell's equations without the imaginary unit. And what we are saying is that there is no way to write quantum mechanics keeping Hilbert space structure and tensor product structure without the unit I. Now you can of course say, I don't want Hilbert space at all, I want Bohm's model, I want path integral. And then, yes, you can do it. If you change the entire structure, you can avoid the I. But if you stay within Hilbert space and tensor product of Hilbert spaces, there is no way to avoid the complex numbers.
Thank you.
I think it was suggested that if a quantum measurement is made, let's say here, right now, the speed with which the information about this measurement spreads in the universe might not be infinite, but finite. But then in that case, there would be, it would say that, that there is a preferred basis.
Yes.
So is it not better to have it spreading at infinite speed and not require this preferred basis? Because that would be more consistent with special relativity.
Do you prefer chicken or lamb? It's not a matter of what you prefer. Anyway, nature will decide, so we should do an experiment, and nature is going to give us the answer. It's not to us to decide, I prefer that one or I prefer this one. We have to look into every possibility, provided these possibilities make predictions.
Okay, thank you.
Yeah, any more question? Yeah, please.
I just wanted to ask one little thing. So when we talk about Bell's inequality and stuff, so we talk of non-locality, and that is like spatial, right? So if we were talking about locality, like it's non-locality in space and stuff. But if we have a Hilbert space, we can make it like Hilbert's part of like space part, like space-time part, and then the spin part and stuff like that. So when we talk of non-locality, why can't we have the spin part, the spin part can do whatever it wants, right? It doesn't have, it can be, 10 miles away from each other. I don't see how the spin being non-local has got anything to do with like the space part, because it is a different part of the Hilbert space, right? So.
Well, indeed, I mean, you can violate Bell inequality using spins or using polarization or using, as Harald also showed, this path entanglement. And you can use time-energy entanglement. So you can use many, many degrees of freedom. And according to quantum mechanics, it doesn't really matter. It could be angular momentum and so on. And in all cases, you should be able to violate Bell inequality. And actually, I think all the degrees of freedom that I just have mentioned have been used in different experiments to show that you can violate Bell inequality. Now, you were mostly saying, so spin doesn't have a position, so if we use spin to violate the Bell inequality, there is no non-locality. Still, there is non-locality because one spin is under the control of Alice, and the other spin is under the control of Bob, and Alice and Bob are at a certain distance, at a large distance, let's say large enough that it's clear which measurement outcome provides from Alice and which one comes from Bob. But maybe I didn't understand your question.
I didn't say, I agree that there should be non-locality and stuff because of the Bell's inequality. What I'm trying to ask is, can we, just look at the spin part, or should we ever, when we just look at the spin part and do observations on spin in any way, and since spin doesn't depend on position, can we, so how can we talk about non-locality when we're talking about a part of the Hilbert space which is not related to space? So that is the question.
Because you will have a Hilbert space describing Alice's spin, and there is another Hilbert space describing Bob's spin, so that you have two Hilbert spaces, one attached to Alice, one attached to Bob. So that even if this Hilbert space is just two-dimensional, like for qubits, so of course qubits don't have position, but nevertheless, Alice is controlling one of these qubits, and Bob is controlling the other one. So maybe I'm not fully... Do you have something more to...
All measurements all said in an opposition measure.
Yeah, you can say at the end it's all position measurements, but I mean, of course we think in terms of measuring, for instance, the polarization of a photon, but of course we measure that with a detector which is maybe here, and another one which is located there, so that detectors of these polarized photons have a position. The detectors have a position, even if we're measuring polarization in this example.
All measurements are meant collapse of position of the point at the end of the day.
Yeah.
But at least detectors have positions.
Yeah. Any further? Yeah, please.
Yeah, hello. Thank you for a good talk. I think that last question was about the entanglement of the spin degree of freedom with the spatial degree of freedom. Not a bipartite entanglement particularly, but for a typical example of a Stern-Gerlach, the spin degree of freedom gets entangled with the spatial degree of freedom. And for an analogy, we can consider the apparatus pointer basis is entangled with the system basis. So that is the question I thought, and I would also like to ask there what you have to say on such kind of entanglement of different degrees of freedom. Instead of spin parts getting entangled or the momentum parts, the two different degrees of freedom are getting entanglement, and what the Bell inequality has to say about it.
Well, I guess indeed the theory says that you could indeed have one qubit made out of polarization of a photon, and the other qubit could be a path entanglement or could be a two-level atom. And you can have entanglement of all kinds of degrees of freedom. And experimentalists, we can test many of them. But in order to really get motivated, if you want Harald to do now an experiment, I don't know, entangling a photon, a polarization of a photon with a two-level atom, he can do it. But to motivate him, you have to come with some predictions that would be, you know, to make the story interesting, because there are too many possibilities. You can, I don't know, you have 1,000 degrees of freedom and 1,000 degrees of freedom there, so you have 1,000,000 combinations, and we're not going to test 1,000,000 of combinations just to keep us busy. We need a prediction, and if we have a prediction, I'm sure we will do the experiment.
But in the typical Stern-Gerlach kind of experiment, there is an unitary evolution happens in the spatial part, right? As we see that two different trajectories will lead, and yes, in the z direction, yes. And those should be connected causally with each other, right? There is no spatial separation, means space-like separation.
So we can maybe move to next.
No, I mean, if you have just a single quantum system, then with many degrees of freedom, I mean, you can make some pseudo tests of a Bell inequality, I would say, and I mean, you can connect those tests to contextuality tests or something like of that sort. But I mean, you do not see any signature of locality or non-locality if you just have one quantum system. And therefore, I mean, these systems, these experiments would give you completely different answers. It's not about non-locality anymore.
Okay, thank you.
Yeah, please.
In fact, hello. So for the single particle, if one entangles two different degrees of freedom, like say spin or path, like one of the experiments of Weinfurter, then you can derive Bell inequality by assuming non-contextually. Yes. So that to tell some interesting physics.
Yes, but this was done already. But I mean, it's just it does not, to my knowledge, not go beyond. I mean, it's a nice point of view at the beginning. But it does not tell us about locality.
It has no bearing on non-locality, but it's for a single part.
Yes,
so it has no bearing on non-locality, but it has its own. It's now called the single particle intraparticle entanglement. Its various applications and its various conceptual.
Yes, in this
so
respect,
that's a different kind of implication. So quantum non-locality can occur in different places. Another classic example is in measurement process. In fact, the Schrödinger-Cat paper, where Schrödinger talked about both his cat paradox, he also made that famous statement, entanglement is the characteristic trait. That was in that paper, he discussed both measurement problem and non-locality, and discussed entanglement. As an answer. I find that paper very, very interesting.
Definitely.
And also in any discussion on non-locality, why one should also refer to measurement problem and all this.
But it's again very long, and it's three papers, and nobody reads three long papers.
But I would strongly recommend, but anyone can come back to it again and again to understand how he connects it.
Yeah. I have one question to Harald. So as you have in your slide, you are showing that this measurement independence loophole that has been closed in several ways, taking color source from distant galaxies. And Nicolas, in his talk, this network non-locality, he was mentioning that this, in a sense, this measurement independence assumption, instead of that, here it is source independence assumption has been taken. Yeah. So is there any experimental way to ensure that source independence assumption, what it can be done for measurement choice?
Not quite sure whether there would be one. I mean, I guess that will remain some assumption then.
I see.
Because because, I mean, you assume, what if I understood you correctly, and if I speak instead of you, is you have these hidden variables, these lambdas, again determining. And if these lambdas come from some common origin, then you are not sure about their independence any longer, or they are not independent.
So, any further question? Please.
Hello, very nice talk. So
Yeah,
I would like to.
Okay, please go. Just wait. Next to him.
Okay, so very nice talk. So I would like to ask on the single particle entanglement. So I work on that field and cryptography. So there, like Weinland showed, like how we entangle the electronic part and the spatial part, and the state looks like exactly the Bell state. So we have two. The composite system has the spatial part and as well as the electronic part.
In front of your mouth.
Oh, sorry. Yeah. So I would like to say that the entanglement created by Weinland group, it was just like two Hilbert spaces composite subsystem. One is the spatial, another is the electronic. It just exactly looked like the bipartite entanglement we see in two systems with same degrees of freedom, say polarization in two photons. So I would like to know why this would be a pseudo like Bell state. Why won't be just a
No, pseudo. I mean, it's not a Bell theorem test any longer, okay? Because we do not have non-locality. I mean, I like these experiments. Actually, we did one of those experiments already, still in Innsbruck, actually. So before 2000. It's very nice experiments. It's from the conceptual nice, I would say.
Right.
But it does not test. It cannot test non-locality. It can test contextuality.
Okay.
But we cannot, and therefore it's good for something.
Right.
But we just have to put it into the correct position, and use the results in the correct context then as well.
Right. So cannot we have a one-to-one correspondence between this? Because all that we do is like we measure something and we count some A and B, like Professor Nicolas said. So cannot we just see two different like subsystem and predict something and then make a table of all prediction and get the non-locality, like non-locality test? In a single particle level, I mean.
Yes, contextuality, for testing contextuality of quantum physics, I guess it's very, very well suited.
Okay.
We have to use it for the correct purpose where it is defined in this context.
Okay.
Yes.
So I'm not sure whether this is what you have in mind, but there is one thing that you can do also, is to have just one photon, for instance, on a beam splitter, and when it goes either here or here, or actually more precisely, it goes here and there, and then you have a single photon entanglement. So you can have an entanglement that involves a single quanta, a single photon, but of course the two subsystems that are entangled is this optical mode gets entangled with this optical mode. So you still have two systems, but the systems are not the photon, the systems are the optical modes. And you can have entanglement between two optical modes, and with that you can also violate the Bell inequality.
Okay, so how about we just have a single photon and the different degrees of freedom of it, like the polarization as well as the angular momentum, let's say, or the path?
Exactly. So if the photon goes this way and that way, you cannot measure polarization because the polarization is not here or there. So you need to do more sophisticated measurements. It's actually essentially, the qubit is between vacuum and single photon excitation. So you have on both sides you have vacuum and single photon. Oh yeah, that is very useful. Thank you. Yeah, so this is possible, but then you need to, if you have this single photon entanglement or single particle entanglement, you can violate the Bell inequality, and then it has to do with non-locality because you again have really Alice and Bob, but then you need to measure a degree of freedom which is appropriate for this kind of experiment.
Right.
And this is non-trivial because you have to measure something which involves the vacuum. Right. So you need a local oscillator and so on. So it becomes technologically difficult to do, but it is feasible.
Okay, yeah.
Yeah, or you let two quantum system absorb this superposition state. I mean, that's then but then you transfer it again to space, to objects separated in space.
Right.
And therefore, I guess it's well suited then. Then we are back at the initial Bell's theorem.
Right, we can, yes, thank you.
Yeah, very.
Hello. My question is to Professor Gisin. So I'd like to ask, in your slide, you showed one quantum random number generator, which is very small in size. So, I mean, I would like to know how, the quantum random number is generated, and whether we can do Bell's test in, because I believe the sources is not single photons.
Yeah, you're right. I mean, certainly what we have in this little chip, this millimeter-sized chip, is a quantum random number generator, but it is not a device-independent quantum random number generator. And indeed, you are right, we don't have a single photon source. So we have a light source, but it's not single photon. It's very weak light source. So essentially, either it emits a vacuum, so that has no effect, or it has a single photon, and with a smaller probability, there are multi-photons. And then indeed, the stream of random numbers that you get, you need to process them in order to extract randomness. So it's randomness extraction, or you can also call it privacy amplification. So we take a long string and we make it a bit shorter. And by how much do we need to shorten it is by the probability, essentially is the probability of 2 photons. Because if we get 2 photons, then of course we don't get really the proper quantum randomness out. So we need to process it. And actually, I can even continue. We have 2 chips. There is a small chip, the one that goes into these smartphones, the Samsung smartphones. This one, this post-processing is done by the smartphone itself. So we use the smartphone as a computer, as a classical computer. And we also have a slightly larger chip that goes, for instance, into the satellites, the European GPS satellite, Galileo. And there the chip has in itself the computational power to do this randomness extraction.
Yeah. Please.
Wait, may I add in the context of a random number generators, actually I missed this, that the first 3 of the loophole free Bell experiments and actually the last one now also in Zurich, they all have been done with the same quantum random number generator designed by Morgan Mitchell, actually. And this is a random number generator which lives with strong coherent pulses. And so it's the phase noise of 2 consecutive light pulses from a laser diode. And if we believe on spontaneous emission and that the phase of the light pulse then is completely random, so this is also a quantum feature because it comes again from spontaneous emission or a spontaneous effect, which triggers then the laser emission. So in this respect, I would say we can live with even with quantum mechanically created strong many photon light pulses as well.
Okay. Actually, I have one more doubt. In such kind of sources, so how do we verify the quantumness of quantum network? That means multi-photon sources, not exact single photon sources.
Okay, I can invite you to read Morgan Mitchell's paper because he's very serious about all these issues, and it's really like this, that if you have the phase of a laser is well defined, but initially it's completely random, because it starts from a spontaneous emission initially. And this defines then the phase of the pulse. And therefore, I mean, it's a quantum effect which is at the origin of this phase difference. So this is where the quantum origin of the random numbers comes from. And other sources have different systems. So like the beam splitting effect from the ITQ random number generator, or ours has the random time of an emission of a photon. Okay, so it's every one of those random number generator has as its origin a quantum effect, and then I would call it a quantum random number generator.
Okay, Kunika, last one. Yeah.
Hi. So I want to take you back to the place where we were talking about single particle being entangled in 2 degrees of freedom. So I think you said that we can have a Bell kind of test there. But since it's a single particle, so you cannot have the locality assumption. Can you please elaborate?
Well, actually, it's the way that Harald is doing it. So you have, let's think just of a photon going right and left because there's a beam splitter. So it can either bounce, or actually it goes both ways. No, it goes through the beam splitter and gets reflected. Superposition of going one way or the other. But then you could imagine that on both ends you have an atom sitting there and in the ground state, and if the photon arrives, it gets excited. So at the end, what you have is that this atom is in the ground state and that one is excited, superposed with this one being excited and this one in the ground state. So now you have two atoms which are at a distance, in Harald's lab, for instance, and one is excited, the other one is not excited, but it's a superposition of, excited, not excited, or excited, non-excited. And when you can do a Bell test with that in two different labs, that's essentially how you do it.
So we are actually converting it from a single particle 2 degrees of freedom entanglement to a bipartite entanglement and then running the same test.
Exactly.
Yeah, I think we have to now stop here. Let us thank Nicolas and Harald for extending this session 1.5 hours. And particularly to the student, I will say they will be next 3 days, they will be here. Please ask any question, whatever you come to in mind, you can catch them up and discuss with them. One more announcement.
Yeah. Just a minute. I'll request the session chair to give some presents to the two rapporteurs. Some small presents from our behalf. No, it's a cup. It's a cup. Now it's my pleasant duty to give it to this. Okay, a couple of announcements. Now it is lunchtime, obviously. But along with lunch is over about 1.5 hours. You don't need that much time. So you can have a look at the posters, and naturally the poster presenters are requested to make themselves available for most of the time. Now, the next session starts at 2:30.